A container ship entering the Panama Canal measures roughly 32 meters across. The lock chamber is only 33 meters wide. That leaves about 50 centimeters of clearance on either side. Inside that gap, even small forces become dangerous. Wind can push the hull sideways. Propeller wash can drive water along the steel plates. Slow currents drift through the chamber itself. Any sideways movement can turn thousands of tons of steel into a moving battering ram. Electric locomotives prevent that. They run along rails beside the lock walls and pull steel cables from the bow and stern. Each cable holds roughly 1.5 tons of tension. Those cables do not move the ship forward. They hold it in place because the canal does not move ships like a road. It moves them like an elevator. Water rises beneath the hull. Buoyancy pushes upward against the submerged steel plates until the vessel climbs roughly 30 meters above sea level. That lifting force comes from water stored high above the locks in Gatun Lake. And the lake is falling. Rain feeds the rivers that supply Gatun Lake. During drought, that inflow weakens. Rainfall drops by roughly 30%. River discharge slows to about 12.2 cubic meters per second. The reservoir begins losing height. Gatun Lake normally sits near 29 meters above sea level. During drought, the surface drops to about 24.1 meters. 5 meters of hydraulic head disappear from the system. That missing height reduces the pressure that lifts every ship through the canal. The canal still has to lift the ship. The locks work because water stored in the lake flows downhill through massive concrete culverts built inside the lock walls. Gravity drives that flow. These culverts are not small pipes. They are tunnels large enough for maintenance vehicles to drive through. Water drops from the lake into those tunnels under its own weight. As the elevation difference pushes the water downhill, the flow accelerates. Pressure builds inside the concrete passages. Engineers divide that flow through dozens of openings along the chamber floor. Each opening releases a controlled surge beneath the vessel. The floor begins to churn with rising water, not chaotic turbulence. The culvert system is redistributing pressure beneath the hull. The rising column spreads beneath the hull. Thousands of square meters of steel begin receiving the same upward force. The ship rises evenly along its entire hull. If that pressure arrived unevenly, the hull would twist under its own weight. Steel structures this large do not tolerate uneven lift. The culvert system exists to prevent exactly that. But that lift still depends on one condition: height. Lower lake levels reduce that pressure. The chamber fills with a thinner column of water. The upward push beneath the hull weakens, and every lift consumes water. Each ship passing through the canal requires roughly 180 million liters of fresh water. The chamber floods to raise the vessel. When the lock drains, gravity carries that water downhill to the ocean. It never returns to the lake. One transit releases enough fresh water to supply a city of 40,000 people for a day. This channel audits the mechanical failures of global infrastructure. Subscribe to track systems like this as they break under physical limits. The canal keeps spending water while the reservoir refills more slowly. As the lake falls, the water supporting the hull grows thinner. A container ship carrying about 5,000 containers presses thousands of tons of cargo into the waterline. When the surrounding depth drops, the hull sinks lower relative to the lock floor. That floor cannot move. Engineers fixed its elevation when the canal opened more than a century ago. Under normal conditions, a loaded ship floats several meters above it. Drought removes that margin. Steel approaches concrete. But static weight is only part of the problem. A ship inside the canal does not sit still. It has to move. and motion changes the water beneath it. As the hull moves forward, it forces water out of the way. That displaced water accelerates through the narrow side clearances and through the shrinking gap beneath the keel. Faster flow changes the pressure field around the ship. Pressure drops under the hull. The vessel is no longer settling only because of cargo weight. Moving water pulls it lower as it advances. Engineers call this hydrodynamic sinkage, or squat. As depth decreases, the effect grows stronger. The shallower the chamber becomes, the faster the water must pass beneath the keel. The pressure drops further. The hull settles lower while the ship is in motion. A vessel that clears the floor while standing still can lose that margin the moment it starts forward. The safety margin disappears. If the hull settles onto the chamber floor, the full weight of the ship transfers directly into concrete never meant to support it. Avoiding contact requires reducing the load pressing downward through the hull. Containers provide the only adjustable weight. Each container adds mass that pushes the vessel deeper into the water. Removing containers reduces that load. Buoyancy lifts the hull slightly higher. Ships that normally carry 5,000 containers now unload as many as 1,000 before entering the canal. The cargo crosses Panama by rail instead. The vessel enters the lock lighter. Draft decreases. Clearance returns. But the mass does not disappear. Weight removed from the ship presses into cranes, rail axles, and key walls. Only the location changes. Inside the canal, the equation remains brutal. Every lock cycle still releases 180 million liters of water toward the sea. Moving the same amount of freight on lighter ships requires more transits. More transits demand more lock cycles, and every additional cycle transfers stress to another structure. The lock gates. Each gate rises several stories high and weighs hundreds of tons. Two leaves meet in the center of the chamber, forming a V-shaped barrier that braces against the water behind it. When water levels match on both sides, pressure balances across the steel plates. During a lock cycle, the balance disappears. Water stands higher on one side of the gate. Hydrostatic pressure builds against the steel surface. Pressure increases with depth, so the lower sections carry the greatest load. Across the height of the chamber, that pressure creates thousands of tons of horizontal force. The load travels through the gate frame into massive hinge pins buried deep in the concrete walls. Those hinges carry the force every time the chamber fills and drains. Drought changes how often that happens. Ships now cross the canal with lighter cargo loads. Moving the same amount of freight requires more transits. More transits demand more lock cycles. Each cycle forces the gates to swing. Hundreds of tons of steel rotate on the same hinge pins again and again. Bearings absorb the weight. Metal surfaces grind against one another. Stress moves from steel into concrete. Failure does not arrive as a sudden break. It appears as wear. Steel surfaces polish. Bearings deform. Fatigue spreads through the hinge assemblies. The canal continues operating, but every additional cycle shortens the life of the moving parts, and the canal still has to lift the ship. Evaporation draws water from the lake surface day after day. Weak rainfall replaces only part of the loss. Each lock operation releases another 180 million liters toward the ocean. The reservoir keeps falling. The water level stabilizes near 24.1 meters. Every centimeter lost reduces the water supporting ships before they even reach the locks. Modern container ships press deeper into the water through their own displacement. The canal cannot change shape. Lock floors, channels, and gate sills remain exactly where engineers placed them more than a century ago. Ships grow heavier. The water beneath them grows thinner. a container ship enters the lock carrying thousands of tons of steel and cargo. Gravity pulls that mass downward through the hull. The only force lifting it comes from the water stored in Gatun Lake. Near 29 meters of reservoir height, enough water floods the chambers to raise ships step by step across the isthmus. At 24.1 meters, the lift weakens. Ships arrive lighter. Traffic slows. Cargo crosses land instead of water. None of those adjustments create new water, and the canal still has to lift the ship. Gravity pulls the ship down. Stored fresh water pushes it up. As long as the reservoir holds enough mass above the locks, the balance holds and the elevator rises. When that balance breaks, steel meets concrete, and the canal stops moving.